So now we'll discuss what is called as Borel sigma field. Here basically the starting point omega, the universal set is R. The reason for this special treatment given to it is that most of the time we are dealing with omega as R, because what happens is that as we know, we are all statistics people, so we are more concerned about the real valued functions, and so therefore what we are looking at generally, the sample space is going to be either R or be converted into some subset of R, like coin tossing experiment, where the actual universal set is not the R, but we create them 0, 1, 2, 3, and it becomes a R kind of a structure, and we say that we define a mapping. Subsequently we call that mapping as random variable. This is what the simple definition which you learn when you are in BSc, right? So now let's move to what is this Borel sigma field. The definition. It is a sigma field generated by subsets of real line R. Now as it happens, notice that R is and what we require is any sigma field, the omega is a member. And to bring an R, you have to be a little careful. If you take the subset which is finite or countable, then the countable union will turn out to be again countable. Okay, or finite countable union of finite set is again countable. And there is a chance that this R will not be covered in this, and therefore the basic requirement of a sigma field collapses. So to come up over this difficulty, we all know that countable union of uncountable set is uncountable. So why not pick up subsets which are uncountable? So these subsets of R which are similar or let us rub this out. Let us don't bring in the similar, that may create some problem to understand. So R which are uncountable are preferred in this class. So therefore C is naturally the class of intervals in R. Okay. And this is the case, then sigma generated by C is your Borel sigma field. This Borel sigma field plays a very vital role in probability, not only in probability theory but also in statistics, because the very important concept of random variable has been defined using this concept. So that's why this looks to be a very handy and simple exercise, but actually it is not. It is very important from the point of view of, and understanding this, and that is why we are spending a little more time in understanding this and coming back and forth these arguments again and again. The reason being this, that it is not very easy, it looks to be very easy. Now what's the problem which comes in? Now the intervals could be of different type. So the C1 could be AB real such that this is we'll see that it is a collection of all AB R. Then C2 would be C3 could be C4 So these are four. Similarly now, this next challenge is that what we are considering, we have now considered already an uncountable set in the form of an interval, but we are restricting ourselves here to only uncountable bounded set. So there is no rule that the uncountable set should be always bounded. Any subclass or some interval of R need not be bounded all the time. It could be unbounded. It could be unbounded on one side. Okay? So to overcome that difficulty, we will look at C5 class where, and in all this you will add, otherwise that interval will not be defined. Okay? So this is one. Second would be C7 would be and last 8. Okay? So there are 2 of this type and 2 of this type. So this represents an unbounded interval. Now as I change A over R, I get this particular class. And then sigma field generated by that would be obviously the Borel set. Now there is a question of uniqueness. Because what is happening is that there are so many classes which are coming in over here. Okay? So now one has to establish that sigma field generated by any Ci has to be same as sigma field generated by a Cj. And if that is the case, then there is a point. Otherwise, one has to give 8 different definitions of sigma fields, or Borel sigma field, right? So let's look at the first result in this connection. If C1 is equal to I'm going to take the open interval, which is in our, as per our notation, is open interval. So this is if C4 sigma field generated by C, or if C4 and if C4 is a class open interval AB such that A in B in R A less than B, and C says 6 or 8, or C5, which is this one, C5 is equal to, I'm trying to get it which is more not very obvious, so minus infinity to A, what's that? That is C6, right? C6 then sigma of C4 is same as sigma of C6. This is the result. Okay. So let us try to prove this result. Now proof is very simple. You have to show that, this is TST stand for to show that sigma C4 is a subset of sigma C6 and sigma C6 is subset of sigma C4. This, if you do that, then this tells you that the things are done. Okay. So this is something which we need to look at. So let us begin with that. Suppose I have minus n to a. See, this what you have to do is, see, now what you are looking at is this one, open. So I want to go here. So I start with minus on the left hand side. Okay. Now if this is the interval which is open, so this is in C4. There is no justification needed. It's very obvious that being an open interval for every n and a in R. Right? So now therefore this implies minus NA, right, is implied in C4. Okay, no problem, because if the set is there in class, it has to be there in the corresponding sigma field. This further implies, now there is a requirement over here, minus infinity to A in sigma C4. Why that happen? I simply allow to take, this is nothing but the union over n going from 1 to infinity. So this is because now notice that this is n equal to 1 to infinity. Notice that it's a n to infinity, 1 to infinity, so it's a countable union. And being a sigma field, it should be closed under countable union, right? Each one of them is here, and this being a countable union, and since this is closed under countable union, it has to be here, right? So this gets justified. Why this is over here? Fine for A in R. So we got one-way implication that every member which is here is also in the C6 is also a member of C4, and therefore sigma C4 because this is being subset, okay, so sigma C6 is going to be sigma C1, okay. Now to go for the other way around, okay. Now to prove other way around, consider see, in all this aspect, what is important is you should be good in set theory. You should be able to write one set in the form of the other. And only restriction which you are following now is don't run away from countability. As soon as you run away from the countability, you are gone. That's the deadline or a boundary line which you need to follow. Is it going to be crossing that? There are different ways to express, but if you cross that boundary line, then there's no. So whenever you write down something, always keep in mind, can I reach to where I am supposed to reach via countability or complementation? Because that's the only thing which I have in my hand. So therefore now consider minus infinity to a plus 1 over n. Now I am going to construct this interval, right? So this is going to be there in C6. Right? Alright, now if that is the case, intersection of this will be also there. Why this happens? Because A is in R, A plus 1 over n is also in R. So this is also in C6. Now this is because countable intersection. Sigma field is closed under countable intersection. Okay? And so if that is the case, what will happen? If this is here, so therefore the intersection end sigma field generated by this. Because each one of this here, so intersection will be there in the sigma field generated by this. Okay. So now what is this? What would be this? This is actually not this one. You need to remove this. This is direct step is not this one. This is in like what we did here. Directly sigma because of this. So this is sigma generated by C6. Please make this correction. Okay. So but what is this intersection now? The intersection between this, what is this intersection comes out to be? What's that intersection comes out to be? Minus infinity to a. So this is minus infinity to a in C6. Okay? Or is it that or is something else? When I take intersection, see, this is not going to help me anymore because C6 is anyway. So instead of this, now I will look into what else I did not apply. Countable union I already applied. Countable intersection I have already applied. So what is left out? Complementation. So if I consider complement, right? If I consider the complement of this, which is a to infinity, right? Now if I say a to infinity, where does that go? Now this is a to infinity, but this is complement of this particular set. It has to be in, right? See, this is set in C6, complement of that. So you are coming up with this, okay? Because this is a to infinity, which is, this is this, and we have known that this is over there, and so therefore this complement belongs to this particular set. So now Why that is? Because minus infinity to A is in the sigma field, its complement will be in sigma field, right? And therefore this happens. So now, if this is the case, minus infinity to A or minus infinity to B, what happens to this? Huh?
Minus infinity to A, close it or open it? So
It has to be closed. If you make open, this will become closed. Okay? If this becomes open, because now you have to include A, and what we have is open intervals. So I have to bring in somehow that open interval business into picture, and that is why I am trying to do that. So minus infinity to B is this. This is the one. Is in C6. B is greater than A. What does this imply? Minus infinity to A, B. Where does this go? See, this is also being there in the, if there is a C6, it has to be the part of the sigma field generated by this. So if I choose minus infinity to B and minus infinity to A, okay, this is going to be there straight away in sigma 6. Wait. And so what is this after all? This is nothing but open AB. So for every A. So now for every interval AB, it's in sigma 6, 6. Huh?
It will be A and infinity, not open A infinity.
Why?
Intersection.
But which one?
Minus infinity and B intersection A comma infinity.
No. Minus infinity to B, minus infinity. See, so what will be the, this is the one which is common, no? Or this is the one which is common. Which one? We want this. So what we should be writing it? A to infinity. So this is A to infinity. Okay? And so that is why we need this. Otherwise we don't need it. We will be simply getting it out. So this is there. This is already there. Okay? So that is why this is also there in C6. So now what we get is this open interval in so therefore every open interval is and so therefore sigma of AB is sigma of this type of class, which we call it C1, and so therefore this is 1 and this is C4, right? As per our notation it is C4. So this implies C4, sigma of C4 equal to sigma of C6. Okay. So now if you go quickly through what we did, it's very simple. What results which we have used? So points oblique results used. As I told you in the earlier lectures also, that there are some things which we are going very slowly. And now this is a new thing which I add. Though there was no much of a student request from it, but I feel that this is the way, at least for the course like this, which is the toughest course among the entire program, that if you remember a 10th standard book or a 9th standard book, it's the points to remember. And this is the practice I am going to follow henceforward. Of course, with the time race, we have to manage a time so that you don't need to mug the proof. You can remember this portion. Of course, you have to remember it with sequence. Don't mix the two issues. Otherwise, there would be a serious problem and your proof will go anywhere. It becomes a Wiener process, haphazard way, going here and there. Okay? So the first point which we want, claim sigma of, say I will call it Ci equal to Cj. And it is a general case, right? Now to show claim sigma Ci is shown to be subset of sigma Cj, and sigma Cj is a subset of sigma Ci. Okay. So third, then this is claim, this is what we want to show. Now you write sets in Ci and Cj. Express two sets from two classes as either one is a similar type of sets, B. Now let me make it very elaborate. Instead of doing like this, express a set in Ci. Let me put it. Express a set in Ci as A, all right, either as A complement of sets in Cj, B countable union of sets in C, countable intersection of okay. And point number 5, change the role or interchange the role of Ci and Cj. Now what will this step 4 and 5 help? To show these sets are members of sigma field generated by other class. So once that is done, your job is over. So now if you see that there are 6 different steps, exclude this because this is very simple. So 2 plus 2, each one carrying each step carrying half mark. So that constitutes 2 marks and 1 mark for writing correct claim. So that makes it the 3 marks question. So try to write this down. Otherwise, as I pointed out earlier, that it is extremely difficult to mud these many theorems and lemmas. So, and now if you have this particular stuff ready, this is not only up to Borel sigma field equivalence of 2 different sets and so on. Given that anywhere that the sigma field generated by say class C1 and C2, this C1 and C2 will may be arbitrarily defined, then if you follow like this, then you are on to get the answer. Now, even some step here and there, here or here, step number 4 and 5 are very crucial. It is observed that you cannot express one set in the form of the union, intersection or complement of the sets in the other class, then you say that, oh, these 2 sigma fields may not equal. And this is what is useful in checking prove or disprove type of question. Prove or disprove, these are the 2 classes such that this. Then the sigma field generated by the C1 and C2 are equal. They could be equal, they could not. Now the best thing, now once you start following this and you observe that somewhere here or here you could not, then you start search for a counter example. Okay? And that gives you a hint that, this may not be true. There is no point in scratching my head and working it out and spending time. So you simply write this sets cannot be expressed. And see, there are 3 possibilities. If you can show neither of this happens, you are done. You can easily say, no, this statement cannot be true because I cannot express. Fine, if you cannot express this, you cannot stop because that's a half answer. Because these 2 are still pending. Okay? So you have to be a little bit more methodical. Okay? So what I will do is, I'll ask you to go back and do it for, I think there are plenty of students in the class. So make the 2 combinations, takes other 2 sets. Say for example, we have done say C4 and C6. Anybody can take C1 and C2. Somebody can take C3 and C4 and do it. Okay? If you have any difficulty in tutorial class sometime, we will come back and do that. Okay? So we have to keep a time race also in mind. We cannot spend more time in identical things to be done. Okay? If you don't do it, please don't be hesitate. Come to me. I'll try to explain to you. Okay? For that, you have to use Bia's Butt book. In Butt's book, what they have given is that how one set can be written in the other side. So this portion is available. You have to polish like this. That's the only part which is required. So what we are going now to a concept called probability. And there is a funny stuff moving around this particular world. Okay? That people are saying we are learning probability from standard 8 or standard 9. What's the new thing? Okay? See, when I have made a query I used to get, even today I get those queries. Let's see, your MSc syllabus, probability distribution is fine. Your calculus, real analysis and those things are fine. But why there is a probability theory? We are already learning from FY BSc. Why we have another probability theory coming in here? Student doesn't know that what they are trying to look into is a different way of looking at probability, and what we are looking at is the foundations of probability theory, or more precisely the mathematical foundations. Why some exercise which we do in a probably undergraduate class or any other classes like probability distribution, those steps work. That's the way we are trying to find out. Now, we define, if you remember, we define probability of an event. Now, event is a set. What probability does? What probability does? Let me know what is your impression. What it gives you. When I say some probability of this event is this, what does that understands you? Or if I write a table, I can probably write it down to call it as a probability distribution in the formulation. And that is quite correct. The values and the probability. So what does that table gives you? Chance of occurrence is the one which the model has point of view, but think it logically. What probability does is exactly what we people do with you. It ranks the outcomes. Who is most likely, who is next most likely. Now to do that, there is a method. There is a score attached. There are events and I am getting score. A is having probability half. What it means? This set has probability equal to half. So this fellow has been given 50% score. Like we give A grade, B grade, O grade to student, individual student. But now individual student and the score, this is a different ball game, because there is a one identity and that identity has been mapped onto one number. Now knowingly or unknowingly, probably what we are doing, we are mapping a set onto a number. This aspect we never learned in undergrad. So what you are dealing is nothing but a set function. It's not a real valued function. Though it appears, its domain, codomain is real value, fine, but its domain is a collection of sets. And that's what you need, that set should be feature enough. And that is why this set function is defined on sigma. And that is why we need a creature called sigma field. Getting the point? Why so insistence on sigma field? Why there's a trouble? Why there's so much topology is bombarding on you and so on and so forth? This is a reason. So we all know there are three approaches of probability. First approach was of course relative frequency or classical approach. Then second was model assignment, right? And third one was obviously action. Now the probability was defined long back. There's a Fermats and other people who talked about probability in different notions. If you look at the probability, say Poisson distribution, Poisson and these people, and and go back to their time span, it was much, much earlier than probably today what we think. But when I tell you the probability theory is not very old, okay, the axiomatic approach is which is very common nowadays. Now what does the axiomatic approach say? If you remember, it says that there is a function which assigns the mass to events A with following properties. So what is that function? How does that function comes? How did it exist? That time it is clearly only mentioned like this. Okay? But now that basis, that set function is called as measure, and therefore the concept of measure comes in, and therefore we call a measure theory as a foundation for probability theory. Tomorrow I'll quickly go through what is a measure, how it is defined, and then we come back to when we put some restriction on the measure, it becomes a probability or probability measure. Okay? That's done. So Borel in his very famous paper in 1935 establishes that probability theory in some sense is a particular case of measure theory. Measure being converted into a typical measure, a set function is such, and assigns a mass 1 to entire properties. P of 1 as 1. In general, the measure doesn't assign a fixed mass to. Now, if there's a fixed mass, the finite mass is assigned to omega, that measure is called with a different name. We'll come back and see that. So, in 1935, the famous paper which gives a mathematical foundation for the actions or axiomatic approach. Now people start talking about, then it is very particular, then all statistics becomes a particular case of mathematics. But why there are separate departments? The reason for that is what is called as concept of independence. That is not existing in mathematics. Whatever the dependency, whatever is we can talk about is a mathematical relationship. See, I'll give you a very simple example. If you talk about, you all have proved it in SYBSC probably. I proved it in SYBSC, so I'm sure that's not gone above, it has gone below. It might have been proved in FYBSC. X bar and S square are independent. Am I right? Somewhere you must have proved. Sample mean and sample mean square, or what you call that, S square. Now if you see mathematically, both are functions of x to x to x. So mathematically they cannot be independent. They are related. But our case, so that tells you that this independence in statistics has something different to do with independence in mathematics. So that is done. Now interestingly, in 1913, Markov has already proved that there are certain sequences which do not observe this sequence also. They are dependent, statistically dependent. And that is what today we are very famously called as Markov chains. And if you see the machine learning, this is occupying a key position, Markov theory, Markovian theory. Okay? And that's something which, because that is for the first time, it did not use the word system learns. But for the first time, it says that next step is going to be dependent upon what has happened in the past. Till then, people were talking about IID. Everything is independent of everything. But he is the one who first established that, okay, there are systems or sequences which they do depend on idea. And when they depend on idea, it is a decision, what we call, I have learned from the experience. And the first machine learning model, if you treat human beings or the system as a machine, it learns. And that's what Markov has, all this should be contributed. I don't know how far people give attributes or contribution to get the credits to Markov, but in our opinion, Markov is the one who first suggested the concept of machine learning, though he doesn't know. So now there are three approaches. We all know this approach collapses when there is no equal likeness and independence. Similarly, this approach collapses if there is no finiteness of sample space. Sample space could be countable. And so, therefore, this fellow is very commonly used. This approach. Okay? So, now we are focusing on this approach and try to show mathematical feasibility of this particular approach which we are taking. So towards that, we have to define the concept of measure. A measure is set function defined from sigma p to r plus positive half of it. In other words, you can say that it's some kind of a set function. I will take a non-negative value. Of course, with as we already mentioned, u of phi as p0. Okay. Then 2 if a1, a2, an are disjoint sets, mutually exclusive sets, then mu of union so sum of the measure of a union in sum of the measures of the union. And if they are not disjoint, this is less than or equal. Okay. Similar thing happens if I remove a1, a2, an as some ai, I went from 1 to onwards and countable collection, and this is called as finite additivity. And this is called as finite stability. So there are certain restrictions on this. When we go to probability, we have something more coming in. Okay? Now, if you have mu of omega to be finite, this is called as finite measure. And if mu of omega is not finite, it's called as infinite. So here, the mu of omega will be any positive number. It need not be 1. That's the difference between a classical measure. I will see tomorrow the example of measures. What are those? And couple of them are very frequently coming in our statistical theory, and we are using that every now and then. In fact, some of the distributions are coming out of those measures, okay? And those can be converted into probability measures suitably. Okay? So I think we will stop here for today and continue tomorrow.